since this is the first talk of the workshop, I thought maybe I would mention a few general things. I hope it's not too boring to the experts. So what I will present is joint work with Benjamin Harrop Griffith, sorry, Jacob Bedrosian, who's in Maryland, and Benjamin Harrop Griffith, who's at UCLA. So here's my outline. First, I will discuss a little bit the physics of vortex filaments. Then I will explain the mathematical challenges that we faced. I will state our result, and finally I will give a few ideas of the proof if time permits. And of course, I should say, you're most welcome to interrupt me anytime. Talks on Zoom tend to be a bit unpersonal, so feel free to interrupt me as much as possible. So let's start with the physics. So the set of equations that we consider is the Navier-Stokes equations in 3 dimensions. So they come in 2 formulations, either under the velocity formulation, where the unknown function is u, the velocity, and it's a divergence-free field, or in vorticity form, where the unknown function is omega, the vorticity, which is the curl of u. And the vorticity form has the advantage of canceling the pressure term, which was present in the velocity form, but it comes with a few additional difficulties. In particular, it's the other way around. The Biot-Savart law allows you to recover the velocity from the vorticity. So u and omega are swapped here. Okay, so this is going to be our set of equations. This picture is meant to illustrate what vortex filaments might look like. So, don't try this at home unless you're an expert vapor. But you have many such nice pictures on the internet. And I guess the idea is that these sort of structures are usually described by vortex filaments that I will define in a second. And they're seen to be stable in many situations. So these are relevant physical objects. And even more so, beyond such nice pictures, it's believed to be important in the dynamics of incompressible flow. So what is a vortex filament? A vortex filament is a solution of the Navier-Stokes equation for which the vorticity is concentrated on a one-dimensional curve. So this is what a vortex filament is, and this is believed to model, such situations. And so this is a little bit the sort of picture we have in mind. Well, now this comes with an immediate problem, which is that if you try to plug such a solution in the Euler equation, which is Navier-Stokes with 0 viscosity, then it's easy to see that the equation doesn't make sense, no matter how you try to write it. So it's not possible to make sense of the Euler equation for solutions whose vorticity is concentrated on a 1D curve. So, you need to desingularize, modify the equation, maybe prior to letting the modification parameter go to 0. But at least to start with, you need to regularize the equation to make sense of it. So there are 2 options. Option 1 is to stick to the 0 viscosity setup, but to thicken the vortex filaments, which do then become vortex tubes. The problem is that you're dealing with Euler equation, which is more unstable than Navier-Stokes. So plan B is to turn on the viscosity, so to take a positive nu, it's certainly more physical, but of course it tends to blur the shape of the filaments because the vorticity is going to diffuse. So they're not going to remain concentrated on 1D structures. They're going to diffuse immediately. But of course, if nu is very small, this will take a very long time before you see the difference. We choose plan B. So we will take positive viscosity and we'll try to make sense of the equations. Okay, so there are two ways of looking at the problem. One is staring at the filaments very closely and look at the microscopic structure. And the other one is to see from far away, in which case we'll discuss the macroscopic structure. So let's start with the microscopic structure, which is the Lamb-Ozeen's vortex. So it's a 2D structure. So in order to describe it, I just retain the unknowns x1, x2, and everything is invariant in the z in the vertical direction, if you want. So everything happens in a horizontal plane. And as usual, this perp sign means that you rotate by pi over 2 your vector. So in the velocity formulation, the Lamb-Ozeen vortex is given by this initial data. So you see, so alpha is just a parameter that gives you the strength of the vortex. And you notice x perp of x squared. And as time goes by, the viscosity, which is present in the flow, will regularize this initial data, which obviously is singular at 0. So this will translate into this regularizing factor that vanishes at 0. Now, this U is not only an exact solution of the heat equation, it's also an exact solution of the Navier-Stokes equation because of a number of miraculous cancellations. It's instructive to look at the picture in vorticity formulation, in which case now the vorticity is pointing in the vertical direction and it has strength alpha with a delta at time 0. And at later time, once again, omega is just a solution of the heat equation, an exact solution of the heat equation. And it's also an exact solution of the Navier-Stokes equation. And you get the usual fundamental solution for the heat equation. So this Lamb-Ozeen's vortex is an exact solution of Navier-Stokes. But of course, the geometry here is a very boring one because everything happens in 2D and the vertical direction is just invariant. If you translate in the vertical direction, nothing happens. So this corresponds to the case where the vortex filament is actually a vortex line. And in this case, you get very nice exact solutions. But of course, trouble happens as soon as you try to bend the filament. And you don't want a line anymore, but rather something with curvature. We'll come back to that later. So that was for the microscopic picture. So what happens very close to the filament. Now, if you're very far away from the filament, you'd like to say something about the dynamics of the filament. In 2D, it is possible. So here is the picture. So the data is given by this time not only one delta function, but a number of delta functions. And there is a regularization step where you desingularize the equation, as I mentioned earlier, but then you let the regularization parameter go to 0 so that it doesn't have to appear in the equation. There is no viscosity present here or no vortex tubes. So I omit this regularization step. And what happens is that at the initial time, you have this bunch of delta functions with, strength alpha I and position pi of 0. And then at time t, you have a bunch of delta functions with the same strength, but they moved. The positions are now pi of t. And the dynamics of pi of t is given by the Helmholtz-Kirchhoff equations. So it's a nice Hamiltonian system in finite dimension, which tells you how these point vortices talk to each other and interact. So there is work on this question, of course, by physicists, Helmholtz and Kirchhoff, and then it was rigorously justified by Marchioro and Pulvirenti, with subsequent important work by Gallet. So in 2D, we understand everything. We understand microscopically, you have this Lambos in vortex, and macroscopically, you have this, this nice point vortex dynamics. Now in 3D, the situation is more complicated and very poorly understood. So here is essentially the conjecture. So suppose initially the vorticity is concentrated along a curve gamma naught. So delta gamma naught means surface measure carried by the smooth curve gamma naught. Alpha is the strength, so it's just a real number. And tau is the vector, which is the unit vector, which is tangent to the curve gamma naught, because the vorticity is a vector. So it's supported on this curve, on this filament, and it has a direction which is always tangential to the filament. And that's needed if you want omega to be divergence-free. So the conjecture is that if this is your data, if you regularize, so maybe you add viscosity, or maybe you thicken the tubes, and then you let the regularization parameter go to 0, you rescale time properly, then what you should observe is that omega at time t is given by same thing, except that now the initial filament gamma naught has become gamma of t. And of course, the interesting thing is what's the equation satisfied by gamma of t. I need to recall what a Freinet frame is. So if you have a curve in three-dimensional space, the Freinet frame is given by tau, which is tangent to the curve, n is the normal, and b is the binormal flow. So it's usual, one-dimensional differential geometry. And then dynamics are conjectured to be given by the binormal flow, which works as follows. If you take a parametrization of the curve, then the time evolution of this parametrization is given by kappa, the curvature, times the binormal flow. And this goes back to the beginning of the 20th century. It was proved in physical terms by Darius, who was a student of Levi-Civita of differential geometric fame, of course. Okay, so that's the conjecture in 3D, and there is little rigorous mathematics to support it. It seems difficult for the time being to prove this, but this is the expectation. And so the binormal flow is a beautiful geometric evolution problem. For instance, circles are solitons for the binormal flow, and the binormal flow is equivalent to the cubic NLS equation through a certain transformation. It has a lot of beautiful properties. Okay, so I hope this was reasonably clear. Now I would like to discuss what are the mathematical challenges associated to this situation. And I should say mathematical challenges, pertaining to our aim. So what is our aim? We'd like to construct solutions of Navier-Stokes with data which are vortex filaments. So maybe the most general situation would be the vorticity being supported along the curve gamma naught. And you might want to add a smooth perturbation. And this problem is in a way comparable in difficulty to the problem of perturbing a straight filament. So that's what we set out to do. If you want, before you can even prove convergence to the binormal flow, you'd like to make sure there exists a solution. And this is not obvious, as I will try to explain. Okay, so our aim is really to just show that the problem is locally well posed for some time, or even more basically to show that there exists a solution. So I will try and explain why classical mathematical theories around the Navier-Stokes equation are not enough to achieve this aim. First thing to try is weak solutions. So either Leray theory or generalizations of it, which do not ask for finite energy, but locally finite energy. Well, it's easy to see that this is not going to work because the data, in the case of a straight filament, is not locally L2. So there is no local finite energy. So there is no hope of applying anything like weak solutions, Leray solutions, to this problem. Okay, well, if weak solutions do not work, let's try strong solutions. So the first framework was Fujita-Kato, and then Kato's theory. So Fujita-Kato was for H1 half fields, and Kato's theory for L3 fields. But well, same thing. The data that we are facing doesn't belong to H1 half log or L3 log. The optimal result as far as local well posedness goes was achieved by Kor and Tataru, and it gives an optimal functional framework to get local well posedness. And this is requiring that the data belongs to gradient BMO, meaning that the data is a derivative of a BMO function. BMO is like pretty close to L infinity. And if you can check actually the data U0 in the case of a straight filament, but it's the same if the filament is curved, can be written as the gradient of a BMO function. So Kor and Tataru's theory seems to apply. Well, until you read the fine print, not only should you belong to the space gradient BMO, but you should either be small in this space or belong to the closure of Schwartz functions for the topology of this space. But this is not the case for us unless you are in a perturbative regime where alpha, the strength of the filament, is very small compared to the square root of the viscosity. So Kor-Tataru's theory applies if you take alpha sufficiently small, but of course the regime of interest physically is if alpha is large, and this is not covered by the theory of Kor and Tataru. So to summarize, none of the existing general theories suffice to give a solution to the Navier-Stokes equation with the data that we're interested in. Actually, there is a good reason for that. It's related to this conjecture by Gia and Chirac that non-unique solutions of Navier-Stokes can arise from self-similar data. So if you take data that are invariant for the scaling of the equation, and the Ozin vortex is certainly one such data. If you take data that are invariant for the scaling of the equation, then they conjecture that actually the equation is not locally well posed, the solution is not unique, everything breaks down. It has been proved by Buckmaster and Vicol that non-uniqueness holds at a lower regularity around the energy space. But Gia and Chirac conjecture that actually you can go all the way up to the scaling. So to summarize, the idea is that scaling invariant solutions should be sort of the boundary between order and local well-posedness and everything nice, and chaos where we don't control anything. Of course, not all self-similar data, but at least some self-similar data should sit on the boundary between the region where the equation is under control and the region where it's getting crazy. So it's not a surprise that if we want to deal with self-similar data, as is the case for the lamp-Ozin vortices, or locally self-similar data, as is the case for vortex filaments, we're gonna get into trouble because these are locally self-similar. So you need to analyze them very carefully to be sure that though they are locally self-similar, they don't cause a major catastrophe, as is conjectured by Gia and Chirac in some cases. Right, so this is what I just said. Locally self-similar data are expected to be on the boundary of local well-posedness. If they're small, then you should get local well-posedness. This is coherent data result. And if they're large, then strange things could happen. This is the conjecture of Gia and Chirac. And this explains why there is this smallness condition, here. If you're in a perturbative regime, then things are fine. But if not, the problem becomes hard. And here the sign is, should be the other way around. Right. Now in 2D, you might ask, does the same problem arise? And the answer is yes. But somehow in 2D, the geometry is much more favorable. Locally self-similar data or I should say exactly self-similar data are naturally of the type just given by a delta function, because if you take 1 over x squared, this would be the natural type of scaling invariant data, but it's not locally integrable. So pretty much the only choice you have is to put a delta function if you want self-similar data. And for such data, local well-posedness could be proved. There is a number of important works, Gallet-Wayne, Gallagher-Gallet, and Gallagher-Gallet-Lyons, who proved various types of local well-posedness, uniqueness results for such data. So once again, in 2D, the situation is well understood. But in 3D, there are a lot of problems. I hope I was clear. Please, feel free to ask if anything was not clear. Right. So now, and that I hope I convinced you that this is a delicate problem. Let me state the results that we obtained. Right. So once again, this is joint work with Jacob Bedrosian and Benjamin Howard-Griffith. So let me start with the case of a straight vortex filament. Essentially, what this theorem is saying is that the Lamb-Ozin vortex is stable, and the equation is locally well posed around it. So if you take the Lamb-Ozin vortex and you perturb it, then you can find the positive time for which you have a solution, and the solution depends smoothly on the data. And furthermore, it takes the following form. The solution at time t is given by the solution that we saw for the Lamb-Ozin vortex plus a smooth perturbation. So it's a result about stability of the Lamb-Ozin vortex solution. Now, maybe the more interesting statement is about the well-posedness around the curved filament. So now we consider the more general case where the initial data is given by, so as we saw earlier, alpha is the strength of the vorticity, gamma naught is a smooth curve, and delta sub gamma naught is the surface measure carried by this smooth curve, and tau is the tangent to the smooth curve gamma naught. So we look at data which are of the form for the vorticity. This is the vortex filament, and then we add a smooth perturbation. So actually, whether you add the smooth perturbation or not doesn't really simplify or make the problem harder. Most of the problems already are there for the smooth vortex filament. So what we prove is that there exists a positive time for which Navier-Stokes has a unique solution in an appropriate class, which depends smoothly on the data. So there is a kind of local well-posedness. And furthermore, it takes the following form. So at time t, you get the, so this is just the smooth vortex filament, which you convolve with the fundamental solution of the heat equation. And then, the smooth perturbation remains there. So how should we understand that? What this means is that, as expected, the microscopic structure of the solution is given by the Lamb-Ozin vortex, which you fit on this curved filament. Right? So the Lamb-Ozin vortex in principle is given by straight filament. So the vorticity is supported on the line. Now, what you can do to cover the case of a curved filament is essentially to bend this Lamb-Ozin vortex, and then you get the solution. So of course, it's easier said than done, because the Ozin vortex is an exact solution in the case of a straight filament, but not anymore if you bend the filament. So if you bend the filament, then there are error terms that appear and that you need to manage. So this theorem confirms, the expectation that, well, first there exists a solution, it's unique, and second, microscopically, this solution looks like the Lamb-Ozin vortex. Then you're going to ask me, what about the local induction approximation, which is to say the conjecture that if you scale appropriately the parameters, you can converge to the binormal flow. Well, I must confess we're far away from that. First of all, because the time over which we control the solution depends in a very bad way on the parameters alpha and nu. And so in the regime in which you should see the local induction approximation or the binormal flow, in this regime, in terms of alpha and nu, t converges to 0 very quickly. So there exists a solution for short time, but the time over which we control the equation is not enough to justify the local induction approximation.
May I also ask you, this is Boris Kesin. So it looks like this also shows that the vorticity propagates instantaneously, right? Just because you have the heat canal. So it means that whatever...
The vorticity propagates, sorry?
Instantaneously. So you immediately have the effect of this motion everywhere in the fluid.
Yes, but this is to be expected if you look at Navier-Stokes, right? If you look at Navier-Stokes, you have the heat equation inside, yeah. So it's going to diffuse. This...
Right, but but when we have a filament, we kind of expect some different.
But yes, of course, if you look at Navier-Stokes like we did, you need to deal with that you're diffusing. But of course, if nu is very small, you're diffusing very slowly, so you will retain the appropriate geometric structure for a very long time. The other option is to look at Euler and then thicken the vortex filament to get a tube, but things are then very unstable. But of course, it's also a very interesting direction.
Thank you.
Okay, so let me try and mention some ideas of the proof. So let's start with the straight vortex filament. So then it's a classical idea that you should consider self-similar coordinates, because the solution is locally self-similar. So if you rescale space and time in a self-similar way, it is certainly going to help. So xi is the rescaled space variable, tau is the rescaled time variable, and capital omega is the rescaled vorticity. And then we consider the following decomposition. So once again, we're looking at the straight vortex filament. So initially, the vorticity is supported on a line. And then as time goes by, what you see is the Lamb-Ozin vortex. And then there is stuff that is going to come, because of the perturbation that you put initially. So not only do you have the Lamb-Ozin vortex, but you also have a so-called core contribution here, which lives at the same scaling as the Lamb-Ozin vortex. So what this is really saying is that if you want to perturb the Lamb-Ozin vortex, then not only do you need to control things on a scale 1, but you also need to add an error term at the microscopic level at the scaling, which is that of the Lamb-Ozin vortex. So what we do is we take the Lambosian vortex, we perturb it at the initial time, and then for positive time, you have a core contribution which is very close to the vortex and which lives at the same scale as the vortex, and you have a background contribution which lives at scale 1 and which is smooth. And our task is going to be to control these core and background contributions. So for the core, you rescale the Navier-Stokes equation, and what happens is that okay, so there are a number of terms coming up, and if you rescale the heat equation, what comes out is this operator, which is the Fokker-Planck operator. Oh yeah, I should have said. Sorry, I'm stepping back. What I should have said is that in order to fit the geometry of the Lambosian vortex, we rescale only in the horizontal direction. So we rescale only the distance to the center of the vortex. But in the vertical direction, in the z direction, we don't do anything. And this corresponds to the sort of intrinsic scaling of the Lambosian vortex, which is invariant in the z direction, but in the x horizontal direction, depend in this singular way on the distance to the center of the vortex. So this is the equation that is solved by the core. Right. So you see there are error terms that come from the interaction of the Lambosian vortex, which is the microscopic part, with the perturbation that you add, and which is the macroscopic part. Maybe I won't dwell too much on this. What's important is if you linearize for the core, you get this set of equations. And so, okay, these formulas are a little bit ugly. What I mean to point out here is that if you linearize, what you observe is that there is this sort of decoupling between the xi coordinate of omega, so this is the horizontal coordinate of omega, and the z coordinate of omega, so the vertical direction of omega. So the horizontal and the vertical components of omega tend to decorrelate in the sense that the left-hand side here is diagonal, and the right-hand side gives a coupling between the horizontal and vertical directions, but it is integrable. It is integrable from -infinity to 0, say. Here I say -infinity because in the rescaled time variable, the self-similar time, if you want, comes from -infinity. So maybe that's a very important observation, that there is this decoupling, and besides this integrable coupling between the horizontal and vertical directions, things are diagonal, and the operators that come up here, gamma and lambda, fortunately have already been studied in the paper by Gallet-Wayne that I mentioned earlier, and a more recent paper of Gallet and Maekawa. So we could rely on these two very nice papers to describe the spectral resolution of the operator alpha times Fokker-Planck plus gamma and alpha times Fokker length plus lambda. And there is a fairly explicit spectral resolution for these operators, which is developed in these papers of Gallet, Wayne, and Gallet-Maekawa. I wanted to sketch a little bit the argument for this, but maybe I won't have time. So what I mentioned tells you what should be done for the core piece, and then there is the background piece, which is more easily dealt with, and this makes sense because all the action really happens at the microscopic level. So what I just said applies to the case of a straight filament. So now, how do you move from a straight filament to a curved filament? Well, the idea is to change coordinates to reduce the case of the curved filament to that of the straight filament. So what is our change of coordinates? Maybe so you can analytically use this formula in more geometric terms. Here n and b are the normal and binormal vectors. In more geometric terms, this is the if you want Lamb-Ozin geometry. This is the curved filament, and you can find a map phi that transforms the center of the vortex filament really itself here into this curved filament. So from the straight to the curved filament. And furthermore, if you take a slice here, which is normal to the filament, it's transformed by phi into another slice here, which is also normal to the filament. So that's, if you want, the reasonable way of switching from a straight filament to a curved filament. So now what you need to do is to pull back the equation, namely to switch from the physical picture, which is given by the curved filament, to pull back this physical picture to our new set of coordinates where the filament has become straight. U, which is the physical velocity, becomes v in these new coordinates. Omega becomes eta. And of course, what's more annoying is that if you change coordinates, you're going to mess up the differential operator. So the Laplacian becomes more general second order operator. Same thing for the curl. And for the full equation, it transforms in this way. So what's very nice, and it has a differential geometric explanations, is that the convection term and the stretching term, they are the same whether you look in the physical coordinates or in the straightened coordinates. But the Laplacian now changes, and the curl operator also has to be modified. So this is a little bit scary because, okay, we have simplified the geometry. Oops, we have simplified the geometry, but we made the problem well, it's not quasi-linear because phi doesn't depend on the solution itself, but it involves differential operators that we understand much less well than we do understand the Laplacian and the flat curl. And one of the saving features in this problem is that if you look very close to the filament, since we chose this change of coordinates in this way that I specified, that slices orthogonal to the straight filament are turned into slices orthogonal to the curved filament. Since we chose phi in this way, if you're very close to the filament itself, Laplacian, the transformed Laplacian equals the Laplacian, and what comes next is higher order terms in terms of the distance to the filament, and same for the curve. So using this key property, it becomes possible to transfer the analysis that was done for the straight filament to the curved filament. And this concludes what I wanted to say. Thank you for your attention.